All right, hi everyone. Can you hear me?
Yes.
Okay. Like Todd said, my name is Kathleen Shea. I'm a software developer for Lawrence Livermore National Laboratory, but my primary position there is to be a core Spack developer, and the biggest feature I've been able to do so far is enabling multi-package parallel builds, which leads to a faster installation, which is very exciting. So. As I'm sure you all know, performance, there are some frustrations around performance, and on this most recent Spack user survey, when asked to rank the importance of adding build parallelism, around 40% of users ranked it as very important to them or critical. And they also, when asked to highlight some pain points around slow installation times, they said build time can be long. If that could be parallelized or shortened, that would be fantastic. And build times are the leading complaint at my organization, and there are slow installations due to limited parallelization. So what's exciting is I did exactly that. we sped up installations by increasing parallelism. So before we can go into what I did to enable these multiple package builds, we should understand what's happening before that happened. So there's a queue of packages that are ready to be built. Once there's a graph of like how package A wanted to be built, and it has 3 dependencies to it. Those 3 packages get put into a queue, and once a package is ready, one sub-process for a package would spawn and start at a time. That would go to completion once that process had go fully to completion, and then we could start the next package from the queue. And this was all done through one execute function, so there wasn't room to start multiple processes with that limitation, but I'll get into that later. So as you can see, where these dependency 1, 2, and 3, there was opportunity for more parallelism, and they're embarrassingly parallel. They could be completely running at the same time without any issues or conflicting things with anything else. So the bottom diagram is kind of to show what it was like before. So the changes in this feature had a few. I'm going to just highlight the main changes because messing with the installer ended up being had a lot happen from it. But there's now a loop that checks the queue for any packages that are ready to be installed like we had before. But now, if there's a slot available to start that package, we start a sub-process to build it. So that single execute command was broken up into 3 parts of starting, polling, and completing the build of a package. And now labeled as P and concurrent packages, it determines the maximum number of packages that can build concurrently. So I'm going to just walk through an example of this algorithm because I think that's easier to explain it. So with this same DAG that we have in the top corner, we're going to act as if we can only allow 2 packages to build at a time. So you can see that there's 3 queues. There are 3 packages in the queue. We check if one is ready, which it is, and if there's a slot available to start a package, which there is. So dependency 1 gets put and the process begins. Then we do the same thing, that there's a package in the queue that's ready to be built. There's a slot ready for that package to be spawned. We spawn it, it starts building. Now they're building at the same time, which didn't exist before. And we're constantly polling these to see when they're done so that as soon as they do wrap up their build, we can just start this same process and add another package building right off the queue as soon as possible. So once one reaches completion, we're still pulling that other one to be done. And we can pop the 3rd package off of the queue in here. And you can already start to see the idea of why this would speed things up, that in the time that the first package is being built, we've been able to start 2 more. And even if it isn't this dramatic as like 2 packages getting to be built in the time of 1, it's at the very minimum starting multiple packages at a time to get that build going. And so once that completes, we're still just waiting for the first one. And then once all the dependency there, same as before, that package can finally install. There's plenty of space for it to spawn, and it's completed. So now that we have this new Spack parallelism of how many packages we can build at a time, we also have to balance that with make parallelism. So like I said again, P is the maximum number of packages that can be built at once, but there's also this J, which is the number of make jobs, which you can think of as like the number of tasks and processes of make dedicated to actually building the packages. So previously, when we were only building 1 package at a time, we would dedicate 16 make jobs to building that package. But if we were to try to do that now, or say we built 4 packages at a time and we wanted to give it 16, that would possibly spawn 64 processes, which most computers can't handle. The overload would be too much, and context switching, like that is not the solution anymore. So we're trying to avoid system overload while still seeing a speed up and having these multiple packages. So how many processes should we be dedicating to each package? Like, what's the ideal place for speed up there? So we collected data on variations of this P and J relationship across multiple types of packages. And this diagram at the bottom here, I think, is a good way to visualize what I was saying about the packages and how we can allocate individual processes to those packages. So then we started some performance testing, like I was saying, and we found that there was a large speed up from one worker process, like one make job, on a package to when we were dedicating 4, but after that, it was pretty much the same speed up. So some packages weren't even benefiting from having 16 processes dedicated to them. And then we secondly found that too many packages with too few workers also resulted in a slowdown. So even though multiple packages is good, if it's too many and we don't have enough workers working on each of those packages, then it kind of takes away the speed up. And there's more of an opportunity for too much overhead and overload. So you can see here, though, that when we increase 2 packages to 8 processes and 4 packages, 4 processes to each one, we're seeing a pretty good curve of lower installation time, lower build times than the one package with 16 processes dedicated to it, like we're seeing at the beginning. So that was very good. However, there were a few outliers. So while overall package build time was reduced, some builds did see a performance penalty. So the examples that I found of this were LLVM and Trilinos, where as you increase the number of packages, it actually started taking more time. And this was very confusing to me, but we quickly learned that it's because these packages are examples of where their build being slow is not as much about that they have multiple packages trying to build at once. It's that they have one giant package that needs a lot of work to be done. So when we were taking away the processes that could build those independent packages, then if we're just focused on that one package, the majority of the build, and we have 8 of those processes like blocked off, or whatever, how many of the processes blocked off for other packages, but those aren't really, that's not happening at the time, then we're seeing a decrease in performance. So we ran into a load balancing issue of, okay, well, it's not super fast when we do one package and there is room for parallelism, but if we try to make this the default for everything, it's gonna have some packages slow down still. So that led to the need of a make job server implementation where there is no generic blueprint for every build. All package builds needs are different. And the job server is able to dynamically allocate jobs to packages. So instead of us trying to figure out what the perfect balance would be, this job server is able to do that. So how it works is you initialize a pipe with 16 tokens, or in our case, 16 tokens, and each token represents permission to execute one make job. So this is through an acquiring and releasing token system. You can also think of this as like reading and writing, but acquiring and releasing makes more sense to me. So a job begins and a token is acquired to know that it has permission to build those jobs. And then those tokens are efficiently managed and reused as the tasks are completed. So once the job is done with the work it needs to be done, it's immediately released back into the pipe with tokens, and that means that another job can be started with that slot. So this also prevents system overload by limiting the number of jobs running in parallel. It's always going to be a maximum of 16, and even if there's more work to be done, those jobs are just waiting to be deployed. And you can see this diagram at the bottom of the pipe, tokens acquired, those jobs run, it's released back into the pipe, it goes back, and we just keep rerunning this cycle. So one issue of this is that, I expect to see a speed up, and in a lot of ways we did, but for examples like LLVM, the job server it's pretty much the exact same time as what it was before this feature, but it's still significantly faster than when you're taking its resources away to try to build multiple packages at a time. So that's pretty confusing, but our new theory as of this morning is that it's because LLVM actually doesn't use make to build, it uses Ninja. And this is a good time to highlight that right now we only have the job server implemented for Unix systems, and we're still working on doing it for Windows and Ninja, or different makes. But for make packages, we did see some pretty exciting results. So here are some final runtime performance improvements. So in the blue, we have the develop section with the sequential builds that I showed you at the beginning, and the orange is our parallel builds with the job server. So we're seeing benefits from both multiple packages that has that beginning work done, and also dynamic resource allocation. So it's the hypothetically most optimal way for us to be dedicating these processes to multiple packages building at a time. And all resources are being utilized without our previous fear of overloading the system. So I'm very excited about that. The installations will be much slower. You guys can expect to see this very soon and hopefully have less time building. And with that, thank you. Sorry I went really fast.
That's great. All right. Leave the performance up.
So true.
Okay. Any questions? Okay, we've got lots of questions. I guess I'll start with Bill.
Hey, have you looked at the kitware fork of Ninja that supports make job servers?
Yes, we have. However, we wanted to start with just doing this Unix approach.
No, this is Unix.
Oh yeah, sorry, yes.
Yeah, so.
We just haven't tried, we haven't experimented.
We just,
Yeah, it should just work.
Oh, okay. Well,
Yeah.
Great. I'll look into that.
Okay, so.
And the other question is, what is your, who's creating the job server? Did you write that in Python, or are you using make to initiate?
We used a FIFO pipe, and then we were able to just set the make flags environment to tell it that we're using that pipe, and then it initializes it and uses it.
Yeah, testing with Kitware Ninja is on our list. Like that's the next thing. These plots came on Friday.
Yeah, yeah. This happened on Friday, so the job server is still kind of development.
So you mentioned it only works for Make right now. It doesn't work with Ninja. Have you compared the performance of Make or of Ninja without the job server approach versus Make with the job server approach? Because I hypothesize that it's still faster to build Trillinos with bare Ninja than with the job server approach, unfortunately, because with deeply recursive Make-based build systems, Ninja is astronomically faster. So like for our use case, we set Ninja to be the preferred CMake build system type for all of the packages.
Okay.
So I would be very interested to see that
I have not run
data.
those numbers yet, but I will, and I'll let you know.
It probably won't make a difference for smaller packages, so you're still better off with the job server approach. And I have a second one if I can. Small one is, so with the current implementation where you do the external make-based dep file build, you currently can't, or you have to make clean because of the way that it keeps file system artifacts to flag which packages are installed. Mm-hmm. So for developers, if you install a package and then you change the code for that package, mm-hmm. running make with the dep file doesn't rebuild it. You have to make clean, which induces a pretty significant overhead to re-register all of the installed packages. Mm-hmm. Is that going to be a limitation once this is in?
This, I think will eventually, as we keep iterating on this and implementing this, I think that eventually end of the dep file will be deprecated, and this should be able to solve a lot of those workflow problems that you're talking about.
That was the second reason we did this besides speed, was this can replace dep file. Next. Okay.
So maybe this is a bad question, but what about badly behaving things like Bazel and Python hand-rolled things that don't necessarily respect job servers? Have any thoughts on using things like C groups or something like that to curtail badly behaving things?
So far, I haven't run into or tested those badly behaving packages that you're talking about, but that's a good thing to know, and we can start to look into that.
We haven't done it yet.
Yeah.
We can. I mean, yeah, Bazel is oddly behaved in many ways. So, okay.
Thank you for the talk. This is really exciting stuff.
Thank you.
I'm curious how this compares to, or how this interacts with, the sort of recommended way previously of parallelizing builds, which is spawning multiple Spack installs, using no-hup in a loop or something like that.
I haven't run exactly those I haven't run those comparisons directly yet, but I think that a lot of what was exciting about this was that it's helping the workflow, because when you're just installing things like normal, stuff like that is already happening. We're seeing these performance benefits. I don't know, do you, Todd?
More fine-grained answer is this. The Spack is still managing the builds in the same way. So the top-level scheduler is still in the parent Spack process, and all of the same locking is done there that we did before. So you should actually see faster distributed builds with this. Like, so you can srun Spack installed -p-j and get 3 levels of parallelism out of that, as opposed to just the 2 that you would have had before. So they should go together well, even on a node or distributed, right? As long as your file system supports locking. Okay, I think we have time for like one more question.
Okay, so this might be slightly naive, but okay, generally when you're doing like parallel load balancing, right, you have Amdahl's law still in effect, and so you want to like basically kind of sort things from the most expensive serial task to the least expensive serial task. Is there any sort of like heuristicing that you can do to get better parallel efficiency during the parallel builds of packages beyond just dependency structure?
I think I don't fully understand your question, but do you think with how we're distributing processes, or like those make jobs, I think it would prioritize the ones that need to be built more. But I don't know, does that answer? No, sorry. Are you going to say Ninja? Okay, what are Ninja?
I could point out that, so we don't a priori know how expensive the builds are. And so this handles it dynamically like the make job server would. But actually, Caetano's going to be talking today, tomorrow. Yeah, and so he has a lot of data on how fast builds are. And so one interesting idea that we're not going to talk about, but that you could think about, is you could tag the packages with some of the data from his statistics that we get from CI, and then do fancy scheduling things. I don't know how you would integrate with Make's job server, which is essentially a FIFO in the file system. But anyway, we could think about ways to make it smarter. Or do you know how we would do that, Bill?
In C-test, we kind of do that. So if you did have some sort of ranking of length of build, if you started, say, LLVM, say you've got 10 packages, 9 of them are kind of small zlib sort of things, and then LLVM. You want to start LLVM first, because you draw the graph and it's going to be building LLVM and then the little packages. So if you could order the things by large, you want to start those large ones first is basically the trick.
Yeah, for sure. Well, thank you guys for all those questions. They're great. And if anyone wants to talk to me again, I'll be at the conference the next few days. My name is Kathleen Shea. I'll be around. So thank you.
Let's thank Kathleen again.